So in order to generate a load scenario, you have, I'm going to do it for one day in the moment where you do it more or less perfectly. You are given the temperature predictions for, in this case, for Boston on a particular day. You're given the description of the humidities, which in some ways is kind of funny here because I don't see why the humidity would drop at 12 o'clock, but that is what is part of the data. You are giving at the wind surface, and you are given the cloud cover, which is useful especially in the winter. And from that, you are supposed to come up with a load. The load being the demand for the electricity. So you will look, the load at time t will be determined by the evolution of the temperature up to time t, the humidity, the dew point, the cloud cover, the wind, and you do this for every t between 0 and 24. And if you have a clever method, you will produce a particular load for that day. Okay? That is simply a transformation from information that you get to information of what the consumption will be. But when you have that, it doesn't capture any uncertainty. It says this is what you will get. And what should we actually see? What we actually should see is something like this. There's a middle tendency, and then there are many possible paths that the load may evolve during the day. In mathematical terms, this is called a stochastic process, because you look at the evolution of the load over time, and you say, this one is maybe the overall tendency, but there are many, many other. This one is not so likely, this is more likely, and so on and so on. You have a probability distribution over these trajectories and these paths. Here it's an artistic description because we don't know, but that is what we really want to look at. So how do we get this process? We're going to have the segmentation. We're going to look at the season or subseason and the day characteristics in order to produce a segmentation of the data in the subseason. The next step will be to, from this information, to derive the overall drift, what we showed as the overall tendency in a moment. And how do we do this? And then, excuse me, I went too fast. I will be estimating the volatility around this drift, overall drift, and it will be evolving over time. The next step will be how to carry out all of this information. We will want to also have the dependence. For example, if it's been warm at 10 o'clock, we'd expect to have the continuation to be different than if it is cool at 10 o'clock in the morning. And finally, the dependence on the evolving state. This is in some way a way to describe in words what people would call a stochastic process. Now, what is a segmentation? The way we create enough of these segmentation is by creating the Wednesday rule and zone rules in order for us to beef up the data so that we don't have simply predicting if it's a Wednesday. No, we will have a transformation going from every day to Wednesday and from Wednesday to every day. We will have seasons, and this is in some way somewhat heuristic, but there's a basic cluster analysis that takes place. In the spring and the fall, it be mostly dependent on the temperature, but there are other factors like surface wind will enter into it. In the winter, it's mostly temperature and cloud cover that are important. In the summer, it's temperature and humidity or dew point. And then the predictions have to be made for wind and solar power, which are more complicated. They are handled independently, and if we have time, we'll say a word about that. The result of doing this segmentation is that of the data is that per year you only get 20 to 30 days. And consequently, you are very poor in data. Okay? If you go, let me try to take an example from somewhere else. Suppose you are a statistician and they ask you to find the probability distribution of a certain event. And this is an event which is maybe just the height of people or whatever, or the number of telephone calls or whatever you want. And instead of the 250 points that they require, you say, I only have 7 points. They will send you home.
No.
No? They won't send you home?
No. On the basis.
That assumes that you already have a prior, which is not the data, it's not part of the data. The data comes only in 7 points. They will send you home. You have to use, and just the remark was very well taken, you have to use some additional information. And there are many ways to do that. The way we do that, we say, okay, you have hard information, which are the observations you have, and we have soft information. And the soft information can come in many, many, many forms. And we have developed the mathematics to actually fuse hard and soft information. It's a very interesting subject. We would take traditional statistics require many, many more observations. So how do we get the mean drift? Well, I give here an example where in my segment, I only have 5 days, and they are in Boston. Having more days would actually complicate the picture. There would be many more lines which would. So I have the temperature for the 5 days. I have the humidity for the 5 days. And now from day D-1, which is the day before, I want to predict the load. And what I do is I create a regression which tries to fit a combination of these two pieces of information to the loads which were observed on those days. These were the loads which were observed on those 4 days, and I'm going to give somewhat of an expression that you minimize in some way a curve which will minimize, which will be a function of the predictions, but which will get as close as possible to the observation. Now this curve here is actually a Saturday, the observation. By our Wednesday rule, it will be moved to a curve which will look similar to these ones. And then the next step, in order to get the volatility, we'll get the distribution of the errors. We'll take the drift, the overall drift, and see how much error there is hour per hour, and we will get, in that way, a distribution of the errors.